Take it away, Jim.
I'd like to show two case studies of Arctic mid-latitude weather connections. I'd like to acknowledge my two co-authors who actually carried out the case studies. As you know, over half of the sea ice in the Arctic is gone. In addition, there's late freeze up in the Barents Sea and Bering Sea by a couple of months, so the open water can overlap with the beginning of the winter storm tracks. So there's new forcing available for North American weather based upon changes in the Arctic, but the surface interacts with the ongoing atmospheric circulation, so there's uncertainty introduced from that, and I'll show two case studies. There are three processes involved. One is open water sea ice free areas provide surface heat flux, but that's not the whole story. Some people run models without sea ice, but that doesn't include all of the processes. The two other is you need an alignment of the large scale atmospheric circulation, and once the event starts, you can have warm air, heat, and moisture advection into the region that helps the persistence. So the first case is winter 2017 and 18. On the left are winter average surface temperature anomalies of 6 degrees over the Bering, Chukchi, Alaska region. Warm air is less dense, so it increases the thickness between different pressure levels and makes the raises the geopotential heights over the region, as shown in the middle diagram. Is the halfway up in the atmosphere, the 500 millibar height field and contours, and shows the northward movement of a ridge over the Alaska region. This ridge acts with a climatological west coast ridge and sets up a ridge trough pattern over North America. This can lead to cold temperatures over the eastern and central U.S. as shown in the right panel, and this is the warm Arctic cold continents panel. This is a model over the winter of this case study. Warm temperatures shown in red can reach throughout the troposphere, so there's no inhibition from Arctic inversions. Lower down is the heat flux from the surface and shows you can have a winter average of 30 watts contributing to the case. That's not the whole physics though, but it contributes. The other case study is across the Arctic in the Barents Sea region. The blue shows the polar vortex magnitude, and there's a breakdown weakening of the vortex over the greater Barents Sea region around the first of the month of January. Lower down on these forcing terms, the event really starts around the New Year's, and before that, there's 80 watts of upward heat flux shown in red that can help preconditioning the system. Once it starts, there's some warm air moisture advection into the region shown in green, and as noted here, for the 2 following months, both terms are non-zero, and that they add to the persistence of the pattern. So summing up, I've shown 2 case studies. They're event-based, they're regional, they represent region over the area, and the results have a persistence and downstream cold influence both in North America and Eastern Asia, and all 3 processes were involved in these 2 cases.
Jim, are you online?
Hello, everyone.
Okay.
Can you hear me?
Yeah, not very loudly, but we can hear you. Okay, any questions for Jim Overland? Is there anything online? Anything in the chat?
No, and actually, I invite the participants also, if you have questions for the previous talk, you can put them on the chat.
Yeah, okay. Okay. All right. Okay. Can't really think of any brilliant questions. Okay. Thanks for your very convincing presentation, Jim. You've left us speechless.